And so what we think is going on is that these moons are made out of water, ice, and rock. The surfaces are a water ice crust, frozen solid because of the cold temperatures. But below that crust, in between the rocky core, which maybe has some radioactive elements and such, there's a liquid water mantle. Now, we know from exploration of extreme environments on Earth that no matter where you are, if you find liquid water, you find life. And we had a meeting a few years ago with some Earth oceanographers, and they said, oh, water, life, you'll find it. So with that encouragement, we're now really starting to put together an exploration strategy. So on the left is Europa, that's Jupiter's moon, and we are in the process of designing a spacecraft we'll start to build next year to go back and study this moon and see if we can find a place to access the subsurface ocean. The next moon over, Enceladus, is quite helpful. We discovered with the Cassini mission, an orbiter that was around Saturn, that Enceladus is sort of helpfully spewing out its innards. And so there are plumes. You can see them kind of coming out the South Pole there, where the liquid water is being expelled into space. Of course, it freezes immediately, flash frozen. And with Cassini, which was not instrumented for this investigation, we were able to get as far as saying that ocean is habitable. It's got a habitable pH. There's organics. We believe there are hydrothermal vents at the bottom that could be supplying the chemical energy and so on. And so that's low-hanging fruit, right? Titan, another moon of Saturn, is a very interesting place because it has a thick nitrogen atmosphere, but about 2% hydrocarbons. And so it literally rains methane, natural gas, and forms lakes of methane and ethane on the surface of Titan. So that might be a place where you go to look for life that's not liquid water H2O based, but it's methane based. And then the last one in the lineup is Triton, which is one of Neptune's moons, actually also has plumes. And so we want to find out if those plumes are communicating with a possible ocean there. So, sorry, I didn't, you guys probably all read this, but so our goal is to explore these worlds, evaluate their habitability, search for life, and if we find life, we get to compare that life, which could be completely different from what's here on planet Earth, and in that manner, learn more about life here. So, one of the big debates is, well, how do we even recognize it? What do we look for? And so I have a short list of possible biomarkers. It goes on and on. But you've got a spacecraft, you've got limited resources, it's a robot, and what do you actually go look for? What's the payload that you carry? And so that is, right now, the state of the art of debate in our community. And so that brings me to the convergence of science and engineering and exploration. And so we have scientists that pose these questions and describe the measurements that need to be made to answer the questions. But now you need your engineers and your technologists to actually build or even invent those instruments. And if you're going to a place like Enceladus, and this is an image from Cassini showing these water ice particles spewing out into space. Now you need to design a spacecraft that can really, fly through all those jets of ice and collect the sample that you're going to analyze there. You're probably not going to bring it back to Earth. And what kind of hardware and software does that require? And I can tell you that we actually proposed this mission. I was part of a proposal team about 1.5 years ago. It was judged not to be ready, but we got some funding for technology development, and it had to do with being able to tell the difference from new discovery of life and a rediscovery of Florida. So we're working on that. Looking further into the future, of course, what we'd love to do is send some sort of a submersible to the ocean of Europa or possibly Triton. And so that's an over-the-horizon kind of vision, but that's where you start. That's the equivalent of 1971. It really takes a village, not just scientists and engineers and technologists. You need all of those. You also need people who can put together the hardware that's got to last for years in space. There's no coming back for a repair. There's no sending a repairman out there. We need managers to keep us on schedule and within our budget. If we're launching nuclear material, we have to have lawyers to make it through the court process, again in Florida. Obviously programmers. A lot of this is not commercial off the shelf. And when we get our data and we go to our scientific conferences and we make our reports and we write our papers in our peer-reviewed journals, it still does nobody any good unless it's disseminated. And for that we need reporters and educators who can then say, okay, here's where the state of knowledge is, what's next, kids in my classroom. And I'm going to conclude with a convergence that personally I didn't see coming. I'm responsible for the camera on the Juno mission in orbit around Jupiter, and we decided that we would put our pictures out on the internet and invite the public to process them for us. And the art community came and showed up. And I have to say, think back to that little picture of Jupiter I told you to pin in your mind. This is a whole new world for me. And it was brought to me from the perspective of an artist. Thank you.